So more about polynomials here in chapter 13. So we're going to start by talking about a couple of key features about the graphs of polynomials. So the two things we're going to look or talk about here first are the extrema and the zeros for a polynomial. So the extrema are the relative high or low points on the function, on the graph of the function. And the zeros are where the graph crosses the x-axis, aka the x-intercepts. So let's look at an example. Let's say we're asked to locate the zeros in the extrema for this function f of x equals x cubed minus x. To do this, I would use my calculator. If you have your calculator with you, I invite you to take it out right now. We'll follow along. What's the matter?
I'm trying to crack it, but it won't crack it. It's in my lower back, so I don't even know how to fix it.
Okay. So we're going to start by typing the function in. So we're going to press y equals. So I press the y equals button there on the upper left-hand corner. And I'm just going to type in the function exactly like it looks like on my sheet of paper. And then we've been monkeying around with our window here in the previous chapter. So probably all of us have a goofy zoom stat related window. So to graph this, I'm going to press zoom standard. So I'm going to press the zoom button on the top row there and select Z standard. That'll reset my window back to something sensible. And so if I look at what I got, it's like, well, that's a picture of my graph, but I can't really tell what's going on there, right? This part of the graph I'm interested in is right in here. And it looks like it's all the parts in between -2 on the x and +2 on the x. Maybe -2 on the y and +2 on the y. You guys kind of agree with that? Just kind of looking at the picture. So what I'm going to do is I'm going to press the window button, and I'm going to reset my x and y ranges to go from -2 to +2. So the x min I'm going to make -2, and the x max I'm going to make +2, and the y min I'm going to make -2, and the y max I'm going to make +2. And then I'm going to regraph after that. Essentially what I've done is just zoomed in my graph so I can get a better picture of what's going on. Is everybody okay with that? Now, could have you used the zoom command on your calculator? Sure, you could have done zoom in. I usually like to reset my window myself because I like the little bit extra control. So if I know I'm like, okay, it looks like I need something between this and this and on the x and between this and this on the y, I'm just going to pick the this and this myself. I usually get a better control out of what's going on there. So let's find our extrema first. How many extrema do we see in this picture? 2, great. So one of them would be this spot right here, right? What kind of extrema is that? They have names, right? The kinds of extrema. What kind is that one that my pointer's on? We did this first semester. Great, a maximum. And remember, there's 2 types of maximums. What type is this? A local, excellent, yes. As opposed to the other type was global. And I know it's not global because look at all this stuff over here that's way higher than that spot right there. So to find that local maximum, I'm going to press second and then the trace button. And which command does it sound like I would want? Maximum. You're so smart today, guys. I love the participation. At the bottom of our calculator screen, now the calculator is going to ask us for three things. It wants first a left bound. So I'm going to take my cursor on my calculator that's located right here at the origin. And I'm going to use the left arrow button to move that until my cursor is somewhere, anywhere left of that local maximum. That looks like a good spot right there. So I'm going to press enter. Now the question has changed to a right bound. So now I'm going to use that right arrow and just move my cursor somewhere to the right of where I think that maximum is. That looks good. Now I'll just press enter. And then it asks for a guess. As long as there's only one maximum or minimum in between my left bound and right bound, your guess doesn't really matter. So I just usually press enter wherever I'm at. So it says that my local maximum then is the point, negative 0.577, comma, 0.385. Everybody's okay with how I did that in the calculator? Try on your own to find the local minimum. That's this spot right here. So see if you can use your calculator to find that local minimum. Should come up with that number. Did you get it? Yes. Feels good, doesn't it? Okay. The other thing this asks for are the zeros. How many zeros do you see on this graph? Should see 3. Because remember, a 0 is the same as an x-intercept. So I see that my graph crosses the x-axis once, twice, 3 times. Everybody's cool with seeing the 3 now? Okay. To find those zeros, I'm going to use my calculator. So I'm going to press second and then the trace button again. Which command from this list sounds like what I'd want to use to find the zeros? 0! You guys are so smart. Look at that. Again, the 0 command is going to require 3 inputs for me, left bound, right bound, and guess, just like the max and min command. So I'm going to find this 0 first. So it asks for a left bound. I'm just going to move my cursor somewhere left of that 0 and then press enter. Then for the right bound, again, I'm just going to move it somewhere to the right of it, press enter, and then a guess. As long as there's only 1 0 in between your left bound and right bound, your guess doesn't really matter, so just press enter wherever it is. And look at that, I got x equals -1 as my first 0. Everybody's okay with that? Try to find the other 2 with your calculator right now. There's 3 of them. I know the answers already. I'm just writing them down in advance. You're supposed to be trying it on your calculator to see if you can get them. I just wrote it down because I have done this a bunch of times in my life. And I can look at the function and tell what the zeros are without actually having to graph this at all, which is a cool skill to have. You're going to learn how to do that in a few minutes. at least for some of them. This is an easy one to do. Did you get one of the other zeros to come out on your calculator? Very good. I'm satisfied with just finding one of them with the calculator, and you can take my word for it on the other one. Everybody feel okay doing this on the calculator? Excellent. Again, we kind of did this first semester also, so it should be not unfamiliar feeling. So one thing that would be nice would be able to look at this equation, this function, and be able to predict how many extrema and how many zeros I should be looking for. Well, we have a theorem to do that. So our theorem says that a polynomial with degree n will have at most n zeros and at most n minus 1 extrema. So what's the degree for my polynomial in the previous example? What's the degree here for x cubed minus x? 3, right? So this theorem says I'll have at most 3 zeros. Here I have exactly 3. And I'll have at most 3 minus 1 or 2 extrema. We see that I have exactly 2 extrema. Now keep in mind, the theorem says at most. So what does at most 3 zeros mean? It means you could have 3, or you could have 2, or you could have 1, or you could have 0. At most 2 would mean you could have 2, you could have 1, or you could have 0. It doesn't mean exactly that many. Is everybody good with that? Okay. We'll do some improvement on this theorem as the chapter goes on, but let's do a quick little example here. So let's say we have the function f of x equals 3x to the fourth minus 5x to the third plus 2x plus 2. And we want to know how many zeros there could be and how many extrema there could be. With the theorem that we just stated, we can now do this without having to graph anything. How should I answer this? Let's start with the zeros. How many zeros could there be? What? I would say 4 is wrong because you need something in front of that. You need 2 words. At most 4, or you could have written it as or you could write the list of 0, 1, 2, 3, or 4. Because it says could, not does, could. Everybody's all right? So you have to be careful. Will I mark you wrong if you write 4 instead of at most 4? You betcha. Okay? But I'm telling you now, in advance, that I'm going to do that, so you know to be careful about it. How about the extrema? How many extrema could we have? At most 3. Excellent. I love when we learn from our mistakes like that, right? And again, you could write at most 3, or you could make a list. You could say 0, 1, 2, or 3 for the extreme number of extrema. Everybody feel good on that? Pretty easy to do, right? Not a big deal. What do you have to be careful about? Remembering to write the at most part. but that's, just a thing, right? All right, the next thing we're going to talk about is going to be the end behavior. So again, we talked about this first semester also. The end behavior of the graph is basically describing what the arrows on the graph are doing. Right? When we draw a graph, we have arrows at the ends of it. And maybe sometimes if it's discontinuous, we have arrows in the middle somewhere too. But for a polynomial, you're only going to have ever arrows at the other ends because all polynomials are continuous. Everybody's okay there? So our end behavior is just going to be describing what the arrows at the ends of our graph are doing. To do this, we're going to use a limit notation. So, for example, say we have something that looks like this. So if I look at this, this is the left end of the graph, and I see that that points down, right? So to describe that using a limit, to describe it going left, we're going to say the limit as x approaches negative infinity, and the negative infinity part is designating that we're talking about the left end of our graph. And then we'll say that limit equals negative infinity, and that negative infinity is the pointing down part. So this is describing the left and right. And this is describing the up or down. Everybody's okay there? So if I want to talk about this limit, or this end behavior, this is the right end of my graph. And this one is pointing up, right? So how would I write the limit for that one? I'd say the limit as x approaches positive infinity, because it's going to the right. And then I'll write the name of my function. And then this should equal positive infinity because it's pointing up. Excellent. Everybody feels okay with that? Okay. So we can actually predict the end behavior of a polynomial just by looking at the equation. All I need to do that is the degree of my polynomial and its leading coefficient. So if my degree is an even number and my leading coefficient is positive, we're going to have the limit as x approaches negative infinity. Oops, let's try to make that of f of x is positive infinity. And the limit as x approaches positive infinity of f of x is also positive infinity. Basically what we're thinking here is both ends of my graph point up. Like a quadratic would, that has a leading coefficient of 1. Is everybody okay with that? That's going to be true for all polynomials with even degree and positive leading coefficient. But the way I remember it is just like what x squared looks like. So if the degree is even and the leading coefficient is negative, what do you think is going to happen? This time, both ends of my graph are going to point down. Oops. Come on. Come on. Anytime you want to decide to do some erasing, there you go. Again, just like the graph of negative x squared would look. Is everybody okay there? If the degree is odd and the leading coefficient is positive, well, then the left end of my graph is going to point down. And the right end of my graph is going to point up. Just like the graph of y equals x. That's the way I kind of remember that. If my degree is odd and my leading coefficient is negative, well, that's going to be like the slope of y equals negative, or the graph of y equals negative x. So there, the left end points up, and the right end points down. Is everybody okay with those rules? And the way I remember them is just, I remember what the graph of x squared looks like, negative x squared, x, and negative x, right? I don't try to memorize the rule. I'm just like, okay, if it looks, if this is like y equals x, okay, then it's left end down, right end up. And I kind of remember it that way. You know what I'm saying? Which feels like it's easier conceptually for me to do that. I'm a pictures guy. I like pictures. Some of us are just like at rote memorizers, in which case, do your thing, rote memorizer. That was never me. All right. Let's do an example. So here we're asked to find the end behavior for the function f of x equals 2x cubed minus 4x minus, or 4x squared, excuse me, minus x plus 1. What's the degree here? 3. What's the leading coefficient? Positive, though, right? That's really what I meant. Sorry. So what should happen? What should my end behavior be? The left end should point go back and look at the criteria I just gave you, right? It's just right there on your sheet. Excellent. Yep, the left end points down, and the right end should point up. Everybody's okay with how we did that? Now, we might ask you to support your answer with a table. To do that, I'm going to use my calculator. So what I'm going to do for the left end is I'm going to pick some values for x that get smaller and smaller and smaller, that are heading towards negative infinity. So maybe -10, -100, and -1,000. Now, is there anything magic about these numbers I've picked? No, man, you could do like -8, -13, or -97, -4,082. It doesn't really matter. I'm just picking things that are easy to type in my calculator. Okay, and they're getting like an order of magnitude bigger each time, right? Like I'm just adding another digit each time. And if I do the same thing for my other limit, where we're going towards positive infinity, come on. Does your OneNote ever just like refuse to erase? It just like drives me up the wall. Okay. So to fill in the rest of this table, I am going to use my calculator. So I'm going to start by turning my calculator on, going to the y equals menu, clearing out whatever I had there already, and typing in the new function for my problem. So 2x cubed minus 4x squared minus x plus 1. I'm going to exit out now to the main screen. And what I'm going to do is I'm going to do y1 of -10, y1 of -100, y1 of -1,000, and write the values down into my table. So how do I get to that y1 again? I press vars. I go to yvars. I pick function, and I pick y1. And then I'm going to use -10 and plug into y1. And now rather than jumping through all those menus to get the y1 again, I'm going to just press second and enter. That'll give me the last thing I typed into my calculator. And I'll just go back and update that to make it -100. And then do the same thing and update that to make it -1,000. And then I'll write or copy these values into my table. But I'll do this so I can actually see my numbers. So what I notice is that as x is getting bigger, or I'm sorry, as x goes to -infinity, y is going to -infinity. That's my confirmation. Everybody okay with that? Let's repeat the same process now to do the other table. So I'm just going to use tens instead of positive tens instead of negative, or positive numbers instead of negative numbers. So I'm just going to go press second and enter, and then go back and update my values so that they are 10, 100, and 1,000. And I'll copy those in now. And I'm noticing if I look at the table, as x gets bigger, y is getting bigger. So as x is going to positive infinity, or y is going to positive infinity. Does everybody feel okay with how the table supports my answer there? We remember doing this from before. It's nice that we just got done using the y1 command, so most of us are probably remember where to get that and are comfortable pulling that up and using it, because we had to do it with the last test. Well, I guess we didn't have to, but probably most of us did. All right. So one of the things that we're going to be doing here, or focusing on in this chapter, is being able to solve polynomials, i.e. find the zeros for a polynomial. And we're going to be looking to want to do this algebraically, not just with our calculator. So let's look at how we do this, right? When a graph crosses the x-axis, what is the y-coordinate when the graph is on the x-axis? 0. So I'm going to be plugging 0 in for f of x, which is like my y-coordinate. So this process of finding zeros, and let's make that plus 8, is equivalent to solving the polynomial. Lucas, will you grab the door for me? Thank you, I appreciate it. Okay. I changed the problem. I want to make it positive. You'll see why. Maybe. There's a typo that I found. All right. So to solve a polynomial, the first thing I want to check for is a greatest common factor. Look at the terms of this polynomial, x cubed, 6x squared, and 8x. Is there a common factor amongst those three terms? X cubed, 6x squared, and 8x. Is there something in common? Is there a factor in common with all of those? Let me give you a hint. There is. What would it be? It's not 2, because x cubed isn't divisible by 2. It's, well, that 1 is always a common factor, but there's something other than 1, or negative 1. Don't forget about the variables. It's x. So we're going to factor off an x. Is everybody okay there? Now I'm going to look at the polynomial that's remaining. I notice that's a degree 2 polynomial. What do we call a degree 2 polynomial again? Starts with a Q. Quadratic. I didn't want to say anything because it's a pretty embarrassing oopsie. Spelling is hard, guys. Do you remember how to factor a quadratic from your Algebra 2 class? Well, it's like doing the reverse of FOIL, yes. So you want to end up with something like this, right? So as long as the leading coefficient is 1, you're looking for 2 numbers that multiply to give you the negative 8, and then add to give you the negative 6. What 2 numbers do that? Well, 4 plus 2 is positive 6.
Negative 4, negative 2.
Negative 4 and negative 2 multiply to give you positive 8, and they add to give you negative 6. So that allows me to factor that quadratic on the inside. Does that jog our memories as to factor in quadratics? That's a skill usually we do a pretty good job of in Algebra 2. It's like the one skill you absolutely have to have. All right. At this point, I know that I am completely factored now. Because if I look at each factor, hold on. If I look at each factor, I see that they're all degree 1. Everybody see that? So I know that there's no more factoring I can do. So the factoring portion of this is now finished. what I'm going to do is use the zero product property. What the zero product property says, if you have a bunch of stuff that's multiplied together and that stuff equals 0, at least one of those things has to be 0. So applying the zero product property, we can say set each of these factors equal to 0. Everybody okay there? Now x equals 0, well that's a solution right there. That's done. To solve x minus 4 equals 0, what would we do? Excellent. So x equals 4 is another answer. And then our third answer would be x equals 2. Now, remind me, according to that theorem we quoted earlier, how many zeros could this problem have had? At most 3. How many did I end up with? Exactly 3, right? 0, 4, and 2. Everybody's cool? Let's see an example where we get less than 3 zeros. So this one we have f of x is equal to x cubed plus 6x squared plus 9x. Again, we're looking for 0, so the f of x is just going to be 0. Everybody feel good there? To solve this, what should I do first? I look for a greatest common factor. In this case, that greatest common factor is x. Very good. Now we need to worry about factoring the remaining piece. How can I factor x squared plus 6x plus 9? Good. 3 and 3. 3 times 3 is 9. And 3 plus 3 is 6. Is that fully factored? Good. How do we know it's fully factored? Because every x is degree 1, right? Yes. Of course. So what should I do from here? Great. We apply the zero product property to set them all equal to 0. Well, x equals 0. That's great. I have that. And then what's the solution for x plus 3 equals 0? Okay. And this one? Great. How many zeros did I get? 2, right? Because I got just 0 and x equals negative 3. But we kind of have 3, right? When I get a solution that repeats itself like this, this is called a multiplicity. So for example, negative 3 we'd say has a multiplicity of 2 because it occurs twice as a solution. Does everybody feel okay there? With the term multiplicity, what that means, it's just a duplicate solution. So eventually what we're going to do is we're going to see that theorem before that says at most, the number of zeros is at most n. It's going to turn into exactly n, but it depends on how we count our solutions. So one of the things we're going to have to count are each multiplicity are going to count as a separate solution. And then there's still another piece that we'll address later that we have to count. But if, yes, of course. He is on one today, I'll tell you what. So one of the things that we're going to be interested in is being able to use the graph to predict if a zero is going to have a multiplicity. We've seen in the process of solving identifying a multiplicity, but eventually we're going to want to be able to look at the graph and go, okay, that's a solution that's going to have a multiplicity, because eventually this process gets a little bit more complicated here. So I'm going to draw a couple of pictures here. So this x-intercept, you see how the graph kind of passes straight through the x-axis? We call that type of x-intercept a straight. And that implies that the multiplicity is 1. This type of x-intercept, where the graph intersects the x-axis and then like bounces back the same direction it came from, we call this type of x-intercept a bounce. And the multiplicity here is going to be an even number. So that's a solution that could occur 2 times, or 4 times, or 6 times, or 8 times. We don't know for sure, but it's going to be used an even number of times. At least twice it'll be used. Is everybody okay with that? And the third type of x-intercept is one that looks like this, where it starts bending one way, flattens out, and then bends the other direction. So like if I think about this half, here it's like kind of catching, if I poured water, it would like catch the water. It's like half of a cup. But if I poured the water here, it would like run off like it's the top of a roof. You guys kind of see that? It's called concavity. So if the graph changes concavity at our x-intercept, we call that guy a bend. So that type of x-intercept is called a bend. And that means the multiplicity is going to be an odd number greater than 1. So it could be used 3 times, 5 times, 7 times, etc. Does that feel okay there? So if we go back and we graph that problem that we just did, you don't have to follow along with me right now. I'm just doing this for grins. And I look at the graph. Notice at x equals -3, what are we seeing? Seeing a bounce, because that solution was used twice. And at x equals 0, I'm seeing a straight, because that solution occurred just once. Do you guys see that? So eventually, when these problems get to have lots and lots and lots of zeros, looking at this in advance is going to be really helpful for us to know how many times should I be searching for this solution. Okay. Let's do a little story problem example, and then we'll move on to one more topic. So this example says a company wants to create a cardboard box with an open top. You guys get what I'm saying? Okay. The box needs to have a volume of 500 cubic inches and is to be created by cutting squares from the corner of a rectangular piece of cardboard to create tabs in order to fold up. So what we're saying is We have some rectangular piece of cardboard, and the shaded regions are going to be the squares we're going to cut out, and the dashed line is kind of where we're going to crease to fold up the side of the box. Can you guys kind of see that in 3 dimensions? You have to use a little bit of imagination, but it's not too bad. It says the piece of cardboard is 26 by 20 inches, and we're asked to figure out the size of squares that are cut from the corners in order to create that box with 300 or 500 cubic inches of volume. So let's just kind of write down some stuff that we know or that we're given. And I know that this is 26 inches, and this is 20 inches. And these guys are squares, so I know that like every side length is the same. So I'm just going to do like one of those. Everybody okay with that? Okay. So for a rectangular solid, what is the formula I use to calculate a volume? If I have a box and I want to calculate the volume of space that box holds, how do I do that? Length times width times height. Very good. So what I want to do now is I want to draw in what are the length, width, and height into my picture. Oh, your face.
It's okay. It's fine.
Okay.
No big deal.
All right. Well, as long as you're okay.
Yeah, I'm good.
Okay. So like that dashed line would be your length. This dashed line would be your width. But what would your height be? Be like that part of the square, because that's where we're folding up, right? So that part now becomes vertical, like sticking up straight out. That's like the height. Can you see that? So what I want to do now is I want to find a way to rewrite length, width, and height in terms of x. So that I can solve for x, because x is the side length of my square. That'll tell me the size of the square I need to have. Let's start with the easy one. How do I write h in terms of x? So h is that distance, right? How do I write that distance as an x? What is that distance in terms of x? Just x. Yes, it's like the easiest thing that's ever easy. They're like the same measurement. That's it. Don't have to think any harder about it than that. Does everybody feel okay there? Let's do length next. So that's my length. Everybody's okay there? So I know that this is how far? Nope, not 4x. How far is that blue line? 26 inches. Everybody good with how we got 26 inches? Now, is the length going to be more than 26 inches or less than 26 inches? Less. So we're going to be subtracting something from it. So what parts of that blue line don't we want to count? that part, and that part, right? Everybody agree? So what do we need to be subtracting from the 26? 2x, not x squared. And just subtract x and subtract x again, so it's minus 2x. Does that feel okay? With that being said, now somebody tell me the width. Minus 2x. Yeah. Does everybody feel good? So what we can say then is that that volume of 500 has to equal that. Everybody agree? Okay. To solve for x, what would I need to do first? What's it have to equal? 0. So we'll just subtract 500 from both sides. So far, so good. Okay. What do I do next to solve this thing? Let me give you a hint as the easy way to do this. The solution to this equation is equivalent to what part of a graph? It's equivalent to the zeros, right? The solutions to this equation should be equivalent to the zeros for the graph. You guys buy that? Right? Remember when we found the zeros, we just turned into solving for it equal to 0? Everybody agree? So what am I going to do here? Type it into my calculator and find the x-intercept. I'm not going to FOIL this thing out. I'm not going to try to factor it. I'm just going to type it into my calculator and let the calculator deal with it. Quite frankly, because yucca rooskies, like there's some big numbers going on here, I don't want to deal with it. So I'm just going to type this in exactly like it looks like on my sheet of paper. As an aside, while you're doing that, for those of you that have an ACT in your future, if you run into an equation on your ACT that you don't know how to solve algebraically by hand, just do this. Like get everything onto one side and just graph it and find the zeros. Even if you don't know how to do the algebra, you can always do this. It's a lovely, lovely technique, especially on a standardized test where showing your work doesn't mount to a hill of beans. Okay. I'm going to set my window. I'm going to do this manually. So if I think about it, what is the biggest possible x we can have? Should be 10, because any x bigger is going to make a negative width, right? So I'm going to make my x max 10. X is the length of something, so the minimum it can have is 0, right? Everybody's okay with this? This y is representing a volume, so I'm going to make, again, the minimum value there 0. And I don't really know what to expect here. Let's maybe make the x max like 500 or something. I'm just guessing. It's probably going to get big though. I hit graph. Ooh, it was a good guess. Everybody's good? So we're looking for this value and this value, right? Let's find those zeros. Second, trace, 0 command. I'm going to find this 0 over here first. So I'm just going to move my cursor. Notice that in the bottom of the screen, I won't really be able to tell where it gets left, but the calculator also tells me the location. So all I'm going to do is just keep pressing left until I see the y value go negative. At that point, I'll know I've passed the 0 that I'm looking for. Oh, there, I got a negative number. Press enter. And then just again, keep going forward till I get that y value to turn back positive. Press enter, and my guess. So I have about 1.20. And then let's find the other one. I just pressed something I didn't mean to. Looking for that other one. That's probably fine. Press enter. Oh, it's negative now. Press enter. And 7.02. Sound good? Everybody happy? Not so bad, right? Let the calculator do the heavy lifting for us. All right. One final idea I want to do today, and this is just going to be part of 13.3. This is a pretty beefy section. So we'll do this over a couple of days. So what we want to talk about here is division of polynomials. But before we do that, this process is really the same thing as like taking a fraction and rewriting it as a mixed number. So if I have like 26 over 3 and I want to rewrite this as a mixed number, I'm going to take 26 and divide by 3. How many times does 3 go into 26? 8 times, right? 3 times 8 is 24. I subtract down, and so I'd have like 8 remainder 2. Everybody's okay there? So as a mixed number, I would say this is 8 plus my remainder over my divisor. Usually, a lot of times we write it without the plus between the 8 and the 2/3, but there's really a plus there. I always try to write the plus because I think it gives you the wrong idea. And if you try to type a mixed number in your calculator without the plus, ooh, Boise, did you make a mistake there? Everybody's okay? So what we're seeing here is that if I take some numerator and some denominator, I can do division to get a quotient plus a remainder over the divisor. That's what we're going to be doing here. Now, instead of using numbers, we're going to use polynomials. So let's look at what that process looks like. So I'm going to start by setting up my division problem. What's going to go out here on the outside? Great. The divisor, or the denominator of my fraction. And what's going to go under my division bar. Excellent, yes. The numerator or dividend of my division problem. Now, there's one slight modification that I'm going to make here before we get started. Look at that divisor, the x squared minus 3. What do you notice about that? Seems like it's missing something to me. I go from x squareds to constants. What did I skip? An x. Yeah, so what I'm going to do, and this is really just to make my life a little bit easier and make sure everything lines up, is I'm going to put a 0x there. There are no x's, but I want to make sure I have that place for x's in my divisor. Everybody okay? All right, let's proceed. So now what I'm going to do is I'm going to ask myself the question, what times x squared gives me 2x cubed? What times x squared gives me 2x cubed? The answer to that question is not 2x squared, just 2x. Now that I have that, I'm going to multiply that 2x to all the terms of my divisor and write the answer underneath. And then just like before, I'm going to subtract down. The number one mistake that I see students make in this long division process is not distributing their negative sign. So rather than think about this as a minus problem, I want to distribute the negative and make it a plus problem, an addition problem. So that's going to be the first thing I'm going to do. So I'm not actually going to keep it there. I'm going to make this a plus problem and distribute that negative through. Is everybody okay with what I did there? And now I'm just going to add straight down. So 2x cubed plus a negative 2x cubed is 0. Negative 4x squared plus negative 0x squared is still just negative 4x squared, right? 5x plus 10x is, where did I get 10x from? Shouldn't that be 6x? Great googly moogly, guys. How come nobody's crying bloody murder at that? So that's 11x. And then I'll bring that 1 down. And now I'm going to repeat that same process and ask myself, what times x squared gives me negative 4x squared? What times x squared gives me negative 4x squared? My answer is negative 4. Everybody's good? So I then multiply through And I have negative 4x squared plus 0x plus 12. So far, so good. Going to subtract down. But remember, Mr. Kulik says don't think about it as a subtraction problem. Distribute the negative and make it an addition problem. So negative of negative 4x squared becomes positive 4x squared. And then plus 0 becomes minus 0. And plus 12 becomes minus 12. And now we're just going to add straight down. Negative 4x squared plus 4x squared is 0. 11x plus negative 0x is just 11x. And 1 plus negative 12 is negative 11. So that is my remainder. And I know that it's my remainder because the degree of my divisor is now bigger than the degree of what I have. Everybody see that? That's how I know I'm done. So to write my final answer, I can say that this fraction is equal to my quotient plus my remainder over my divisor. Do some color coding here for everybody. So this quotient, this remainder, this divisor. Do you guys remember doing that in Algebra 2 last year? You should have done that. Whether you remember it or not is always dicey. Now, keep in mind, this is not the only way to do polynomial division. There is a second way to do this. That second way is, in my opinion, faster and easier. It is called synthetic division. Let's see, or let me show you how that works and remind you why we don't teach you synthetic division first. Actually, let's start with why we don't teach you synthetic division first. Why not? If it's faster and easier, why don't we do that first? Because it doesn't work for every division problem. You can only do synthetic division if your divisor has leading coefficient 1 and degree 1. If we go back to the previous problem and I look at our divisor, what's the degree of our divisor? 2, because it's x squared minus 3. Cannot do synthetic division on this previous problem. Everybody's okay? This one, though, we absolutely can. So this is kind of the setup for our synthetic division problem. What number do I put on the outside here? I don't put x plus 3. I put the solution to x plus 3 equal to 0, which is minus 3. Very good. Everybody's okay? What do I put up here? Excellent. So 6, 25, 16, negative 15. What do I have to be careful about when I write those numbers up there? Well, surely the positives and negatives, yes, for sure. But there's one other thing that would have to happen. So what would I have to do if it was just, if I had no 16x term there? Yes, I'd have to have a 0 here, right? That's really easy to forget. You have to be very careful not to do that. Okay. So let's begin this now. The first step is to just bring the first number down. And then we multiply the number on the outside to the number on the bottom. We write it in the next open spot and add down. And then we just keep repeating this process until we have no more open spots left. Everybody okay remembering this from last year? Again, you tend to do this quite a bit, so it tends to stick better than the polynomial long division, which you probably only did for a day and then stop doing it because it stinks. And you don't need to do it very often for what you end up doing next. Now, somehow these numbers tell me the result of this division, right? How do I interpret these numbers? If I start at the far right, that number is the remainder. This is our degree 0 term or constant term. That is our coefficient on our degree 1 term. That's the coefficient on our degree 2 term. And as I move left, I just increase 1 degree, and that's the coefficient on that term. Does that look familiar? So to write our final answer, we would say that 6x cubed plus 25x squared plus 16x minus 15 over x plus 3 is equal to 6x squared plus 7x minus 5 plus my remainder, 0, over my divisor x plus 3. Now, do I really need to write this? No. Why not? Because the remainder is 0, right? There's a 0 over any non-zero number is 0, so it just can disappear. We don't really need it. Okay. This is where we're going to stop today. This feels like enough. Next class, we're going to do, you guys will have a Delta Math assignment.
I only work 2 days, so for 2 days,
So your assignment here would be 1 through 12, 15 through 19. Does this class meet again this week? No. Nope. So what does that mean this is due? Not this Sunday. Next Sunday. Is there anything due this Sunday? No.
Is there anything important that we're doing on Monday?
More of this.
I won't be here.
Okay.